As exploration into the solar system deepens, resupply missions are becoming more and more complex, making 3D printing a preferred solution. For a long time, 3D printers could only print in plastic, but recently, new filaments have entered the market.
So new materials on the market come out daily, sometimes 2 or 3 in a week. We first started off with just ABS plastic and only one size, 3mm. Now we're at 1.75mm and 3mm standard.
With the development of new filaments, NASA and TSGC have given us, ISEN team to NASA, the challenge of determining if 3D printed material can function as an antenna. For this experiment, we selected 2 conductive polylactic acid filaments, commonly known as PLA, designed a pyramidal horn antenna for X-band transmission, which is a frequency range from 8 to 12 gigahertz, and printed it at the Engineering Innovation Center at Texas A&M University.
Conductivity of the materials matters because in order to propagate electromagnetic waves, you have to have some sort of metallic material to go off of. So in the case of the horn antenna, you really need to have a conductive material along the walls of it so you can navigate the wave coming from the waveguide.
When selecting our 2 materials, we focused on conductivity. Conductivity is the ability of a body structure to transmit an electric pulse. After searching the web for the most conductive filaments and getting advice from Jim Wilson, we decided on a graphite PLA by Protopasta that has a conductivity of 6.7 Siemens meters, and F-electric PLA by Functionalize, which has a conductivity of 133 Siemens meters. When designing the horn antenna, we used SolidWorks. This antenna fits the specifications of the 3D printer on board the International Space Station and would not need a support structure to be printed. To print the antennas, we used the Ultimaker 3. 3D printing works by heating up the material and pushing it down a nozzle in a process called extrusion. The graphite PLA took approximately 5 hours to print, and unfortunately, the F-electric filament was too brittle and kept fracturing before entering the printer.
It's brittle because it either A, absorbs too much water, or it has reduced itself, water has been taken out of the material over time.
The F-electric PLA was our preferred material, but due to the time constraint of our projects, we decided to continue testing the graphite PLA. To determine if the antenna could function properly, we conducted an impedance matching test and a radiation pattern.
So for your impedance testing of your horn antenna, you're really wanting to match it to the impedance of your waveguide so you minimize reflections going back into the waveguide of your port. And the radiation pattern is what matters. The whole point of an antenna is to properly navigate electromagnetic energy. So in the case of a horn antenna, you're wanting it to look like a balloon. In this case, your radiation pattern, you're wanting to have it, you do a 360-degree rotation of it in all cut planes usually. For this particular application, it was just important to have the XY cut plane. So you're able to look at the gain in each direction.
After testing, we compared the results to both the metallic and non-conductive PLA antenna. The graphite PLA antenna matched the impedance of the waveguide, but to our surprise, was unable to effectively radiate the signal.
So in the case of this particular horn antenna, it is conductive, but not quite conductive enough to actually direct the electromagnetic energy. The horn kind of sucked the energy to the walls of it, and it acted more as a resistor than an actual conductor or propagating antenna.
Compared to the metallic horn antenna, the graphite PLA radiated with only an average of 9% of the total power. Because of this, we recommend that this material not be used as an antenna. Overall, the Texas Space Grant Consortium Design Challenge was a great learning opportunity. Throughout the course of the semester, we gained valuable experience in working on a multidisciplinary team, self-teaching the SolidWorks program, electrical engineering concepts, and creative problem solving on a budget. During our initial visit to the Johnson Space Center, we got to go on a behind-the-scenes tour of the International Space Station and Space Shuttle training modules. On behalf of ISEN Team to NASA, thanks to the TSGC Design Challenge staff for giving us the opportunity to participate in this competition. As we say at A&M,
thanks and gig 'em.